All right, we're going to go over exponential growth and decay. Now the exponent, our a is our initial value. Okay, it's also known as the y-intercept or y-intercept on a graph. Okay, our b is our growth or decay rate. Okay, and they vary depending if it goes up or down. So when b is greater than 1, we have growth. And when b is less than 1 but greater than 0, we have decay. So in other words, you have a decimal or a fraction, right? And sometimes they actually give us percentages for growth and decay rate. In both these cases, a must be greater than 0. Sorry, b must be greater than 0, and it can't equal 1 for all of this to work, okay? Those are just some side notes. Sometimes they give us growth and decay rates. And the way we'd set a question like that up is we'd have y is equal to wherever we start with. So, maybe we have a population of 1,000 people. So here's our a. And it's saying it's growing by 5%. Well, we have to turn the percent into a decimal. Because what we're going to do is we're going to break this b up into 1 plus the percentage increase for growth, or y, sorry?
Minus 1.
Exactly. 1 minus the percentage decrease for decay. Okay, so let's say we have a city with 1,000 people. So a city's population is 1,000. And we're not sure what's going to happen in the future. It's either going to increase, so we're either going to grow by, let's say, 6%, or it's going to do the complete opposite and decay by 6%. So we're going to set up our two formulas in this case. Okay? So we're going to have y is equal, a is our initial value, which is our original population. So 1,000 times b. Well, b is 1 if it's growing, plus, and our 6% is a decimal, is
0.06.
exactly 0.
You need the years to go for the power.
Exactly. And we're going to figure out what a population would be in a certain amount of years. But here's our equation. So when we simplify our equation, it's y is equal to 1,000, 1.06 to the power of x. And that's a growth formula. And if we're doing the decay one, it's y equals, we still have 1,000 to start. But in this case, it's 1 subtract our 0.06 to the power of x, which actually gives us a value, you're going to notice, of 0.94, a number less than 1, which is why it's decay. Okay, so in this case, our b is less than 1, so we have a decay rate. And if we want to estimate the population, let's say we want to know what it would be in both scenarios in 5 years, well, we replace x with 5 in both of these. Okay, and when we do that, we'll get two very different answers. We'll get one where it grows, so 1.06 to the power of 5 times 1,000, 1,133, so y equals 1,338. And then our other one, we have a value that's going to decrease. So essentially what it's saying is it's going to be 94% of the original population each year. So 0.94 to the power of 5 times 1,000. 733.
Could you say 734 to 0.9?
Well, yeah, you would say approximately, right? And maybe approximately 734. But if we're talking about actual population, we can never really have a 0.8 of a person. So a lot of times in those situations we round down because we don't have a 0.8. You either have a person or you don't have a person, right? And you could say approximately, and we're just making approximations when we're doing this, okay? But notice how this one was an increasing, growing rate, and this one was a decay rate. Okay, and the decay or growth rate, if they give you a value like this, you'd have to discover that it's 0.6. You find the difference between it and 1, and you find the difference between this and 1, and that's how you find those percentage growth or decay rates.